Welcome to Category Theory, the beginner's introduction. I am Martin Codrington, and this is Lesson 1, Video 2 of 6. In the last video, I gave an overview of the planned structure of our explorations into category theory, and I mentioned we'll be applying it to music theory and software design. I also explained the origin of the 12 pitch classes that we will use to build up melody and harmony theoretically. In this video, I'll present a general definition of a category, and the definition of the concrete category we will be concerned with in this first section, the category of abstract sets and arbitrary mappings. I will then begin to explore the definition by taking a closer look at the objects and maps in set. The definition of a category has two parts, the data of the category and the rules these data must follow. First, the data. 1. A set of objects of the category. I will represent objects as colored uppercase letters. In S, the objects are abstract sets. 2. A set of arrows between the objects in the category. The source of each arrow is an object in the category called a domain, and the target of each arrow is an object in the category called the codomain. Example, if we have a function f from A to B, A is the domain and B is the codomain. I will represent an arrow as a lowercase letter, also colored. In set, the arrows are called functions. I will use the term morphism, map, mapping, function, arrow interchangeably. Each element of the domain is assigned to exactly one element of the codomain. The third datum is a special arrow, 1A from A to A, called the identity arrow, defined on each object A in the category. In S, this is the identity map, for which 1A of A is equal to A for all arbitrary elements in the set A. Those were the three data. They must follow three special rules in order to constitute a category. Given two arbitrary arrows F from A to B1 and G from B2 to C, we can form the composite G following F from A to C if and only if B1 equals B2. Example, we can form the composite in the case where we have maps from A to B and from B to C. 2. Composition of arbitrary maps F from A to B, G from B to C, and H from C to D is associative, i.e. the following relations hold. H following G following F is equals to H following G following F. 3. Given an arbitrary map F from A to B, the following identity laws hold. F following 1A is equals to 1B following F is equals to F. That was a definition of a category. You will see different styles of definitions, but they are all equivalent to this idea. Now let's go through each datum and each rule over the course of the next 5 videos in this first lesson, until you understand precisely what they mean. In the rest of this video, we will discuss the objects and arrows in S. The objects in S are abstract sets. Whenever you see an uppercase letter, possibly with a subscript index, I'm referring to a set. Now about the elements of a set. In video 6 of this lesson, we will learn how to formally talk about the elements of a set. We'll actually learn there's no such thing as elements of a set in category theory, in the same way as in set theory. An element is just an abstraction we use to make it easier to talk about sets. What that will practically mean is that we can devise many different abstractions for talking about a set. For example, the idea of a generalized element of a set arises out of this fact. More on that later. For now, we will use a familiar notation of describing a set. If we have a set A of size 2 and a set B of size 3, for example, we will use the following notation to refer to the unique elements of A and B, where the numbering of the elements starts at 0. We will also take the liberty of talking about concrete sets, example C as a set of numbers, and D as a set of pitch class names. We'll be forming our own concrete version of S. We will call this category Music S. In general, a category can have 0, 1, 2, 3, or infinitely many objects. And that's really all we have to discuss about objects in S. All the properties of sets can be described by arrows, and we'll look at those next. The next datum in the definition is a set of arrows between objects in S. An arrow F from A to B is said to have domain A and codomain B. In any category, for an arbitrary choice of A and B, there may be 0 or more possible arrows between them. When we define music S, we must specify the arrows between each object that we would like to consider. Not all possible arrows will be of interest to us. In S, the arrows are maps, also called functions or morphisms. The rule that must be followed for a map to be valid in S is that every element of the domain must be assigned a unique element of the codomain. Terms such as image and value are used to describe this element in the codomain. Multiple elements in the domain may be assigned to a single element in the codomain, but no element in the domain may be assigned to more than one element in the codomain. Let's look at some examples. With the same abstract sets A and B that we described previously, let's construct two valid maps, F and G, with A as the domain and B as the codomain. The map F from A to B is defined as f of A0 equals to B0, f of A1 is equal to B0. Since F assigned both elements of A to the same element B0 of B, we can rewrite the equation as follows. F of A0 equal f of A1 equals B0. This is more than just a shorthand. Assignment relations written this way make the structure of the map more easy to discern, as we shall shortly see. The map G from A to B is defined as G of A0 is equals to B1 and G of A1 is equals to B2. The following thing, H, is not a valid map A to B. H of A0 is equals to B0 and H of A0 is equals to B1. It is not valid for two reasons. 1. It doesn't make an assignment for all elements of the domain. There is no statement for what H of A1 equals. 2. It assigns an element of the domain, A0, to two elements of the codomain. This violates the uniqueness principle. The maps we have just described, F from A to B and G from A to B, are called external diagrams of the maps F and G. They show the domain and the codomain, which is all the theory tells us they must show, but they give us no idea of the internal structure. In order to differentiate F and G, we need to list their assignments, in addition to giving the external diagram. There is another diagram we can draw of maps in S. It is called an internal diagram of a map, or mapping graph. It's important to note that this is an abstraction. It is actually an object in another category. More on both of those statements in the future lessons. But for now, we'll call these visualizations of our maps. If we were to visualize H, which is not a valid map in the category, this is what we would get. With these visualizations, we can now restate our requirements for valid maps as follows. Each element of the domain must be the source of exactly one arrow, whose target must be in the codomain. Notice that in discussing the arrows of this category, we are using the term arrow itself. Remember that for the future. For now, before we start constructing maps of our own, there are just two more things I would like to point out. The first I think should be obvious, but I'll still state it, and it's that the terms domain and codomain are relative and are determined by the map in question. For example, we have defined a map G from A to B, for which A was the domain and B the codomain. But we could also define maps B to A, R for example, for which B is the domain and A is the codomain. R and G, by the way, have a special relationship, and we'll discuss that in Lesson 2. For now, there's one more thing we need to discuss about maps in S, perhaps the most important thing. Consider the following map. We could say that this map was generated by any of the following procedures. 1. J of C is equals to C squared. 2. J of 1 is equals to 1. J of 2 is equals to 4. J of 3 is equals to 9, where we just give the assignments. Or 3. Order the numbers in C by magnitude. Do the same in D. Match the smallest in C with the smallest in D. The next largest in C with the next largest in D. You get the idea. All these processes generate the same mapping in S. One does not have to, and sometimes cannot, represent the process that generates a map in category theory in order to formulate with the map. Maps in S are arbitrary. Nothing generates them, they have no reason for being. All valid maps between sets can be arbitrarily defined and reasoned with. This makes the theory very powerful indeed because we can study systems whose underlying mathematical structure is unknown or difficult to represent, and we can develop tools to analyze any collection of objects and maps without having to worry about what the underlying data represents. This is why category theory can be easily applied to anything, and once you develop tools in one area, you can use the same concepts and techniques in any application. However, this also means that when we define an object in a concrete category, we must be very careful to consider its relationship to all other objects in that category. For example, we need to decide which of the possible maps that can exist actually do exist. And sometimes the same map between sets can mean more than one thing. This is the reason why I take a bottom-up approach to formulating with category theory. I start with the simplest object or objects upon which all other more complex objects are based. I start building up these concepts from this simple object, specifying relationships that must exist and exactly how they must exist, so that when I create more complex objects, the type and nature of these objects are bounded by the rules on the simpler objects. This will all become clear with a real example. We have now defined the objects and the arrows in S. We will have plenty more to say about the arrows in the future, since arrows are what category theory is all about. Objects just exist to allow us to talk about relationships between the arrows. We will explore composition in the next video, but let's end this video by building an actual small category, one that we will keep adding to as we proceed discussing S. This would also start giving us some ideas of what our real form relation should be like when we finish this first section. Let's call our category Music S. We need a set of objects. Let's define X and C, that we have seen as examples earlier. X is a set of pitch classes, the core of all our formulations, and C is a set of pitch class names. We want to keep these concepts separate because, as you can already see, some pitch classes can have the same name, and when we get into talking about sharps and flats as permutations that are inverses of each other, we see that we can have even more names. C natural could be considered B sharp, and we can have double sharps, double flats, and you'll see that in real music. We can even have triple sharps or more, but you're not likely to encounter those in real music. But our theory should still be able to describe them if their use ever becomes popular. Let's leave this for the real formulation. For now, we'll go with this simplification. We could consider many maps between X and C and X. They are precisely 8,916,100,448,256 maps each way. We will learn how to calculate this in a couple videos, but let's define the map that makes the most sense. The map P that assigns to each pitch class is pitch class name. So now Music S has two objects and one arrow. Actually, three arrows, but we haven't discussed the identity arrow yet. But if you think about it, this map is not as basic as it could be. What really is a C#/D flat? Since there are 17 pitch class names, ignoring double sharps and double flats for now, it makes more sense to represent them as a set Z of size 17. And then define a map N from Z to X that assigns to each pitch class its pitch class name or names. Before we go on, let's look at how we can describe the abstract structure of ordinary maps between sets. This will be very important for the future to help us understand the different types of maps we will be discussing in the next lesson, as well as informing intuition for the opposite category and the relationship between maps. From the definition of the map, I claim that there are exactly 12 figures in N, of two types, 7 of this type and 5 of this type. This I can tell from the equations. There are 7 equations with 1 equal sign and 5 equations with 2 equal signs. What this means is that for 7 of the pitch classes, there's only one way to reach that element of the codomain with this map, i.e., there's only one name for that pitch class. The component of the second type tells us there are 2 ways of reaching this element of the codomain via this map, i.e., there are 2 names for this pitch class. In general, we could have figures of the following type. If we have figure of the first type, this would mean that there existed a pitch class with no name. The number of components depends solely on the codomain. It will always be equal to the codomain size, in this case 12, but the types of components are determined by the size of A and the nature of the map. For now, let's call these components clusters: 0 cluster, 1 cluster, 2 cluster, etc. But we can also call 0 clusters isolated elements, and 1 clusters connections. Whenever we define a map, I would like you to picture, by counting the equal signs in each equation, the types and number of components it contains. Now our category is starting to get populated. We have 3 objects and 2 arrows. Let's define one more object and 3 more arrows. This will motivate composition, as we will begin to see that we will need to have a way of combining arrows so that we gain in the information that common sense tells us we should be able to. The set L represents the letter names of the pitch class names. We will define maps Z to L and L to Z. The map T from Z to L assigns to each pitch class name its letter name. Notice that the size of L is 7, so there are 7 components, 4 2 clusters and 3 3 clusters. Now remember, in video 1 of this lesson I said that the major and minor modes are special types of modes that are comprised of pitch classes with one type of each letter name. So we could represent them as 2 sets I, major, and J, minor, as follows. Or, perhaps more useful, we could define them each as maps I and J from L to Z, where each map represents the type of each letter in the mode. Here's a general rule to follow when formulating with category theory. Err on the side of more maps than objects. The theory is perfect for describing relationships between maps and calculating new maps from existing ones. If we define these as sets, we would have to explicitly define maps into Z to match up pitch class names. How else would a computer know that they were connected? Remember, we're going to be implementing this. Whereas, defining them as maps makes the connection obvious. How many modes like this can we form? Modes with one of each letter name. Let's call them regular modes for now. Well, if we go back to the map T from Z to L, we see that there are 2 types of C's, 3 types of D's, 2 types of E's, 2 types of F's, 3 types of G's, 3 types of A's, and 2 types of B's. So that gives us 216 combinations of each pitch class name. But remember, the map N from Z to X told us that some pitch class names match to the same pitch class. For example, if we are developing a new mode and we would like C# and D flat as our types of C's and D's, then we will actually have named the same pitch class. How would we know that? Well, clearly we need to be able to combine the information contained in these 2 maps. Not only can we do this, but it's one of the axioms, remember, we must be able to do this. Since we have, for example, I from L to Z and N from Z to X, we have to be able to form the composite N following I, which will tell us the pitch classes in the major mode. Composition is the topic of the next video, but before we end this video, let's take a moment to talk about how we should express conditional requirements on our maps in category theory. Think positive. Probably good advice for life in general, but that's not what I'm talking about here. As we progress, especially as we consider categories and more structured objects, we will learn a maxim that I will tell you now. Maps preserve positive properties. Positive properties of maps or objects are the is versus the is not properties. While it is true that this triangle is not blue, not green, not yellow, it's easier to say it's red. Okay, that was a simple example, but we, especially programmers, think negatively a lot. For example, in discussing how to create a valid regular mode as a map L to Z, we said, okay, we have to choose one of each type of letter, but we can't choose pitch class names that match to the same pitch class. That we can't choose is effectively saying a valid regular mode can't have 2 of the same pitch classes. It actually seems quite normal to say this, but as we build more and more complex objects, musical phrases, harmonic progressions, if we think this way, our reasoning, and more importantly our code, will become quite complex. Lots of psychomatic branching, ifs, else, and whatnots. Even in functional programming, we can express these ideas more neatly, but not necessarily in a way that makes the connection and the reason evident to everyone. We don't know enough to express our conditions on regular modes yet. I would just like for you to start getting in the habit of thinking positively, and thought that now would be a good time to bring it up. I'll give you an answer now though. If you don't understand it, you most certainly will by the end of lesson 2. A regular mode is any map Mi from L to Z, for which the map T from Z to L is a retraction, and for which the induced composite N following Mi is monic. This is equivalent to saying the following diagram commutes, and N following Mi is a monomorphism. Again, you will understand what all of this means by the end of the next lesson, I promise. But notice that we are able to describe a process which would have taken quite a few words to explain with a simple diagram. When we get to the implementation part, you will see how we can take these diagrams and easily design algorithms that implement them. But first, we must discuss composition, the identity laws, and associativity, so that you understand what it means for a diagram to commute.